Okay, hello everyone. This is Herman Garcia, and these are lectures 8 and 9 from time series analysis. Today we're going to be discussing financial risk and what value at risk is and how to operate with it. So, financial risks can be classified according to Basel into three types. The credit risk, which is default risk, market risk, that is due to changes in stock prices, interest rates, effects, commodity prices. This is the one we are most familiarized with. And three, operational risk. This includes legal risk, this includes political risks, and other kinds. We're going to start studying market risk because A, this is the one where best quality data is available. Second, is the easiest to understand because it's something we have been studying or mentioning already before. And C, because the ideas behind the study of market risk can be applicable to different kinds of financial risks. So we're going to be using these three R packages: extreme values in R, quantization, and computation of value at risks. And so from now on, we're going to let capital L with argument L be the loss variable of a financial position from time t plus L if we let the variable hold for L periods of time. Financial loss is mostly concerned with the distribution of L. All risk measures available in the literature are actually summary statistics from this loss variable. So one important characteristic of risk measures is coherence. We will call a risk measure coherent if for any two loss random variables, call them x and y, the risk of the sum is smaller than the sum of the risks. If x is smaller than y, then the risk of x is smaller than the risk of y. It's positively homogeneous. If you multiply here by a scalar, it multiplies out. And it's invariant translationally speaking, which means if you add a translation value here, it basically translates the curve but not the risk. I mean, additivity. This kind of additivity conserves distribution. So additivity is mostly related to diversification in finance. If you manage to merge several risks together, it's only advisable to do so if you can assure this, that it's actually not more risky to work them together than separate, which kind of makes sense intuitively, right? So, simply put, value at risk is the upper quantile of the loss distribution for a small tail probability. This small tail probability is mostly the signification level that we have been working with during all the course. This is generally either 0.05 or 0.01, and if f sub L is the cumulative distribution function of our variable L, then the value at risk is the upper quantile for probability 1 minus p. I mean, it's the value such that the probability of the variable being greater than it is smaller than p. What does this sound like? Well, it sounds like this. If this is the cumulative distribution function, we're using a probability q here. Yeah, and here this xq, this quantile we're working with here, is the smallest x, such that the probability of being smaller than x is greater than q. So yeah, this is the upper tail for the confidence intervals we have been working with. Now we're going to check this for some common distributions. If L is normally distributed, then the typified distribution is a standard normal, and as such, the value at risk is the greatest tail of the confidence interval. If we choose, for example, p to be equal to 0.05, then this is the normal value. I mean the value that leaves behind probability 0.95 in your quantified normal distribution. The same thing is if the typified variable is a student t distribution with v values of freedom, then we build the confidence interval, and the value at risk is none other than the upper extreme of the confidence interval. It's calculated in this way. And if we have a standardized t distribution with more than two values of freedom, then the value at risk is what it's constructed in the same way. If we are in R and we are using the fgarch package, we can calculate it in this way. Now, consider this subadditivity, where variance of x plus y is smaller than the square of the sum of the standard deviations. You take square roots here, and you have that the standard deviation for x plus y is smaller or equal than the standard deviation of x plus standard deviation of y. Then we multiply by this value, and this exactly means that the value at risk of x and y is smaller than or equal than the sum of value at risk of a and value at risk of y. This, however, doesn't happen in general. You can take a simple counterexample here in Kilkman, Panger, and Wilmot. So, for a small example, we're going to suppose that the cumulative distribution function f sub L of a continuous loss random variable x satisfying these probabilities. So, if we take a significance probability of 0.05, the value at risk of x is exactly 90, because 90 is the quantile 0.95 of x. We can denote this in this way: value at risk at this probability for this variable is exactly this. So now we're going to define two loss random variables, x1 and x2, in this way. And so these two loss variables are truncated version of x, basically. They're exactly these two conditions have to be swapped, okay? And in that case, we'll have x equals exactly x1 plus x2. Since total probability must be 1, the cumulative distribution function f super 1 of x1 satisfies this. So the 0.95 quantile of x1 is 80. Therefore, value at risk super 1 of 0.95 is 80. Here the superscript, here we're using it for x1 because, putting here value at risk sub 0.95 super x sub 1 is actually very quirky. So we're going to use this notation pretty much. And on the other hand, x2 smaller or equal than 0 is exactly a probability that x is smaller or equal than 100, which is 0.97. Such the 0.95th quantile of x2 is less than or equal to 0. We'll denote this in this way. And if we take the sum of the values at risk is smaller or equal than 80. And so if we sum, we get that the value at risk of x is 90, which is greater than the sum of these smaller truncated values at risk. And so if we take x as the sum of these two truncated versions of x, subadditivity of value at risk fails, which is bad. Finally, value at risk does not describe the actual behavior of the loss random variable, so it's not a perfect risk measure. It's good, but it's not perfect. In order to To take care of that, we're going to use what is called the expected shortfall. Expected shortfall is also known as tail value at risk, TVAR, and conditional VAR, CVAR. Simply put, expected shortfall is the expected loss of a financial position after a catastrophe. Expected shortfall of a loss random variable is defined in this way. It is the probability, the expectation of x, given that x is greater than the value at risk. So it's mostly this integer of here divided by the probability that x is greater than the corresponding value at risk. So it's this area divided by the probability that we are here. From the definition, expected shortfall is exactly the expected loss of x, given that x exceeds its value at risk. So for the two densities in the figure, their expected shortfall are different, with the dashed line corresponding to a higher value. Now, let's assume that our variable x is continuous. We let u equal f of x between value at risk and infinity. Then we take differentials. So we have it here. F of value at risk is 1 minus p, and f of the infinite is 1. So x is f minus 1 of u, so x is the value at risk of u. And so equation 4, this equation here, becomes this. Expected shortfall 1 minus p is exactly the integral from 1 minus p to 1 of the value at risk. So this is mostly the average of all values at risk from 1 minus p to 1. And this average is what gives us coherence. So closed form solutions from expected shortfall are also available for some common loss distributions. If our loss variable is normal with mean mu and variance sigma square, then expected shortfall is exactly the mean plus distribution function, partial distribution function of the tail divided by p and times standard deviation. If we have a student t loss distribution, then we have roughly a parallel way to calculate. It's defined in this way. And if we have a standardized t distribution, this small monster over here follows t student distribution, then, well, we still have it. It is already a bit more complicated, but we have an explicit way to calculate the expected shortfall. And so if typified L sub t follows directly a standardized student t distribution, then the equation becomes slightly more easy to calculate, as we don't have to consider this square root in our calculation. So how do we calculate this? Calculation of value at risk involves several factors. First one being build tail probability. In risk management, we use 1%. In stress testing, we use 0.1%. Second one, time horizon L. We use 1 day or 10 days for market risk, and 1 year or 5 years for credit risk. Third one, cumulative distribution function, or its quantiles. We can use either one or the other. In fourth place, the amount of the financial position or the market-to-market value of the portfolio. So, cumulative distribution function, f of L, is the focus of econometric modeling. We can define the loss random variable as here, return if the position is short, minus the return if the position is long. And so the dollar amount of value at risk is then the cash value of the financial position times the value at risk of the loss variable. That's it. Value at risk is value times the value at risk of the loss variable. Okay, there are different methods for calculating financial risk. We have risk metrics, econometric modeling, quantile and quantile regression, extreme value theory, serial collected data. And so, to illustrate the various methods for assessing financial risk, we can consider the daily log returns of IBM stock from January 2, 2001 to December 31st, 2010 for 2,515 observations. We assume a long position of 1 million on the stock and the loss xt is equal to minus rt. This is how the log returns look. So for risk metrics, let's let x sub t denote the daily loss. Risk metrics assumes that the daily loss under the condition of ft minus 1 is roughly, it's a normal distribution with sigma squared variance. Here sigma squared follows exactly this distribution. And therefore, the logarithmic price of the portfolio satisfies the difference equation pt minus 1 is exactly a sub t, where a sub t is an E-Gartz 1-1 process without drift. So the value of alpha, signification level, is generally somewhere between 90 and 100%, with a typical value of 0.94. So for example number 2, we're going to be talking about IBM stock returns. We feed the special E-Gartz 1-1 model of equation 10 to obtain an estimate of parameter alpha. We obtain alpha equal 0.943. So we could be working with a probability of 0.007. In addition, using daily loss after all these observations is this, and with this standard deviation, we can estimate the next standard deviation at 0.7133. Consequently, we use risk metrics. I hope I just didn't turn off the mic accidentally. We have value at risk, probability 0.95 is 1.173. Probability 0.99 is a bit bigger. Expected shortfall is this, and expected shortfall at this probability is a bit bigger. Therefore, our value at risk is our value times the corresponding value at risk percentage, which is like this, and our value at risk probability 0.99 is calculated in the same way and gives us roughly $16,000. Finally, if we assume a holding period of 15 days, we have this value at risk here and this expected shortfall here. Now, risk metrics has advantages and weaknesses. For the advantages, it's very simple. Normal distribution, a square root of time rule. This is here when calculating value at risk. We let it hold for a time of, for some periods, we just multiply here by the square root of them, and that's it. And we can use multiple assets at the same time. And so it's super transparent. However, empirical data generally rejects assumed model. This is bad. And second time, the square root of time rule fails if either of the model assumptions is rejected, which empirical data already does. So it kind of shoots itself. Now let's consider multiple positions instead. For two assets, like asset 1, asset 2, we have that the value at risk is the square root of value at risk 1 squared plus value at risk 2 squared plus twice Pearson correlation coefficient, value at risk 1, value at risk 2. We can generalize this to a position consisting of M instrument in this simple way over here, where rho sub yj is the cross-relation coefficient between returns of the ith and jth instrument, and VARI is the value at risk of instrument I. So I'm going to derivate the value at risk formula for two assets, and then we will extend it to M assets naturally. So let's call R1T and R2T the log returns. The portfolio consists of two amounts, W1, W2, invested in asset 1 and asset 2 respectively. Under risk metrics, we have that the conditional log return 1 is normally distributed with the variance following this model, and for the second one, roughly the same. For instance, for tail probability 0.05, we have value at risk for two assets. The first one is 1.645 W1 omega 1t, and for the second one 1.635 omega 2 sigma 2t. And so we're going to name PT to the log return of the portfolio. This is roughly omega r sub 1t plus 1 minus omega W r times 2t, where omega is this amount, and so 1 minus omega is this other amount. The prior approximation becomes a quality for simple returns. And so for a remark, this is important, because we have invented here an amount W, and it's exactly this. So under risk metrics, we know that our log return is roughly normally distributed with this variance here. Our variance follows this rule. This rule. And so the VAR for the portfolio is W1 plus W2 times value at risk of the log return. For tail probability of 0.05, we have value at risk for the log return is 1.645 times the total money we have invested times standard deviation for log return. Therefore, the square of the value at risk is value at risk 1 squared plus value at risk 2 squared plus 2 correlation coefficient at moment of time t, value at risk 1, value at risk 2, which looks exactly, if you have thought of it, as this. So value at risk behaves mostly like a variance. In some twisted sense, you can actually change this small r with a big R, and so you have the same for any amount of assets. So this result can be generalized for more than two assets in an intuitive way. And second, the formula continues to hold for expected shortfall, provided that the mean returns of the two assets are zero, which is assumed under risk metrics. If the means are not zero, then you have to do some adjustments for the portfolio in order to make the means zero and be able to use risk metrics. For example, number 3, we're going to consider a simple portfolio. 40% is AAA bonds and 60% is IBM stock. The market value of the portfolio is US $1 million. And to measure the bond returns, we employ the daily log return of the Bank of America Merrill Lynch US Corp AAA Total Return Index from January 2nd, 2001 to December 31st, 2010. The data of bond index are obtained from the Federal Reserve Bank at St. Louis. So Like stock returns, bound returns also exhibit the pattern of volatility clustering and weak stationarity. For bond returns, variance is determined this way, for which we have this value at risk over here and this value at risk over here for probability 0.99. Now we recall that for the daily local returns of IBM stock, we have, as we can see in the book, example 7.2, these values over here, we will just use them. And so the sample correlation coefficient of the log returns between this stock and this one index has this value. And so for our portfolio, we have corresponding value at risks, where the superscripts E and B are for equity and bond returns. So this goes for IBM and this goes for bond returns. And so the value at risk for the portfolio is by our square root rule. The square root of first value at risk squared plus second value at risk squared plus 2 times the correlation coefficient times value at risk 1, value at risk 2, which is this number. For this particular instance, we see that with tail probability p equals 0.05, the value at risk is less than the value at risk for each component. 0.07, 0.01, and this is smaller. Okay, this is interesting. So working with these two together, the value at risk decreases actually. So specifically, if we have invested 1 million, the value at risk, if we only invest in one, is roughly $12,000. Only for the bonds, the value at risk is $7,000. And if we work with our portfolio 60-40, the value at risk probability 0.25 is actually smaller than $7,000. This is expected because value at risk is a coherent risk measure under a normality assumption. So diversification actually works at reducing risks. This is great. Now, for econometric modeling, firstly, we're going to use a time series model to predict the mean return, for example, AR cross-section model. And second, use a volatility model to predict the volatility. For example, we can use a GARCH model with T sub V innovations. And this has a problem because it requires human intervention, and also multiple period risk measures can become tedious. So we're going to see how this works. Firstly, with this small example, I'm going to consider again the daily log returns of IBM stock, model 1, a Gaussian arch model, GARCH 111 model. The fitted model works in this way. So the one step ahead predictions at T horizon of 2515 are this for the mean and this for the volatility. And consequently, we have the following values at risk. 0.95 value at risk is like this. Expected shortfall has this form, and same for probability 0.99. These results imply these values, this value at risk, this expected shortfall for the next trading day, roughly. Of course, we are assuming again that we put $1 million there. So for model 2, Gaussian arch model with standardized student T innovations. Then our one step ahead predictions for mean and volatility are this one and this one respectively. And so the risk measures for financial position, value at risk is roughly this, and expected shortfall is as follows. Now, most statistical software provides empirical quantiles for a given dataset. Example 5, we're going again for the daily log returns of IBM stock, considering this, we let L1 be the previous integer, L2 be the next integer, P1 be this way, and P2 in this way. So the empirical 95% quantile of the negative log returns can be obtained in this way, where here xy is the ith order statistic of the loss variable x of t. In this particular instance, x sub 2389 is like this, and x sub 2390 is in this way. And finally, with p equal to 0.05, the sample expected shortfall is $39K. Okay, this is a bit big. Let's face it. Like this is a pretty big amount. Now, quantile regression, I recommend you go to Koenker and Bassett 1978. So we can estimate the conditional quantile x sub q of a variable x sub t given previous conditions this way, where r sub q of beta sub 0 equal a minimum means that beta sub 0 is calculated in this way. Okay, this is a bit cryptic, so we're going to see it with an example. Again, we go back for the daily log returns of IBM stock. We employ the quantile regression with two predictors. First predictor is lag 1 daily volatility, and second predictor is lag 1 VIX index of Chicago Board Options Exchange. More specifically, we're going to consider this quantile regression, where here x sub t is minus the daily log returns, S sub t minus 1 is the lagged 1 daily IBM stock volatility obtained by a GARCH 11 model, and V sub t minus 1 is the lagged 1 VIX index obtained from Chicago Board Options Exchange. Here we use the VIX index instead of okay, I'm losing a word here. And here we use the VIX index, which is important. Okay, so applying the quantile regression in 12 with q equals 0.95, then we have sample beta sub 0 equal this, with this standard error. Beta sub 1 is like this, with this standard error. Beta sub 2 is like this, with this standard error. As expected, the 95th quantile of the IBM negative daily log returns depends critically of the lagged 1 volatility and much less on the lagged 1 VIX index, because this is dependence on the lagged 1 daily volatility, and this is the dependence of the lag 1 VIX index. You can compare 1.17 versus 0.02. Based on the model, we have a sample quantile 0.95 of roughly this, and this implies that our value at risk for 0.95 is roughly $13K. So the red line here shows the 95th quantiles obtained by quantile regression. This plot shows that the value at risk actually varies with time, and so the actual loss may vary when the amount of if the actual loss at the moment expect the value at risk, this has an influence over successive values at risk. That is not that we're here we have a big spike of the loss, then the following value at risk that doesn't follow exactly the loss in return. I mean, predictions are affected by what's happened in the previous step. So now I'm going to stop this here for lecture 8, and I will continue with lecture 9 shortly. We will review extreme value theory, empirical estimation, and other things. So that's it for lecture 8. Please stay tuned for lecture 9. Stay safe, stay hydrated, and have a nice day.